Welcome to Biomaterials. Today we're going to talk about surfaces. And in particular, we're going to talk about how we characterize surfaces. And one of the most important characterizations that we can do of surfaces is a measure of how hydrophilic or how hydrophobic surfaces are. So surfaces and hydrophobicity versus hydrophilicity. Basically, whether something is hydrophobic or hydrophilic. And one thing that we can think about, one thing that we're going to want to think about in these characterizations is how, before we dive too deep into how we quantify hydrophobic and hydrophilic surfaces, we'll first talk about these things qualitatively, but one important thing that we'll need to consider when we're talking about surfaces of materials is how sometimes the surface can differ. The surface can differ from the bulk. And in doing so, and when we talk about surface versus bulk properties of materials, we'll consider two situations. One is where we have dirty surfaces, and then the other where even if there's nothing sort of fouling a surface, we'll talk about how the environment can sort of locally change, even on a molecular level, the surface. So environment effect on surface. Then, after we talk about these things qualitatively, we'll then sort of move on to how we start quantifying how hydrophilic or hydrophobic something is, and we'll talk about the contact angle. And when we talk about contact angle, first we'll talk about two things. First, we'll talk about how it's defined. And then we'll talk about its interpretation as a force for over length. Sorry, this is length. So we'll talk about its interpretation as a force per length. So before we get into that, let's now talk about how surfaces can differ from bulk. So when we talked about metals, we said so for metals. Remember, we said many metals oxidize. When exposed to air. So in that way, we already know that what we sort of observe on the surface of a metal can be very different from what we see. Or if we could sort of transport ourselves into the bulk of the metal, we observe something very different chemically on the surface, right? So basically, if I said, hey, if I have a metal, so bulk metal, we already know from the previous lecture that many metals, not all of them, but many metals, it's thermodynamically, unavoidable if they oxidize at the surface. So what does that mean? Basically, around the full surface of the metal, if I went to touch a piece of metal, right? If I took out a paper clip or anything else, and if I touched that paper clip, I wouldn't actually be touching the metal. I would actually be touching, well, all of the potentially multiple layers of junk that's on top of that metal. And one of the things sort of immediately close to the metal is the oxide layer. So for many metals, we end up with an oxide layer on top of them. And if you think about this oxide layer ends up, well, take a moment now, pause and ponder. Do you think this oxide layer is hydrophilic, i.e. attracts water, or hydrophobic? Well, as we've talked about in previous lectures, things that are very polar tend to be hydrophilic, and this oxide layer is oftentimes sort of an extreme case of something that's hydrophilic. So what does that mean? Well, basically, when the metal oxidizes, right? So if I have an atom of metal, and then I have an atom of oxygen. The oxygen is electronegative, and the metal is less so. So that means that these oxygen atoms end up negatively charged, the metal end up positively charged, and so that basically means that polar water wants to, polar water being very polar is very attracted to this. So basically the water comes in, and the oxygen part of the water is attracted to the slightly positively charged metals, and the slightly positively charged hydrogen on the water is attracted to the electronegative oxygen. So what does that mean? Almost always, even if it doesn't feel wet, almost always surrounding the oxide layer is a potentially atomically thin layer of adsorbed water. So thin layer of adsorbed water. And basically that's because this oxide layer is so hydrophilic that even times it can actually pull water vapor out of the atmosphere to deposit it onto this surface here. So that's how hydrophilic that oxide layer can potentially be. So we have bulk metal underneath it. Then there's an oxide layer due to the unavoidable chemistry. The oxide layer is so hydrophilic that water can even come out of the atmosphere to adsorb to this. I live in a house with a toddler and a preschooler, and let me tell you, there's no surface in my house that is not greasy, sticky, wet in some way. But I mean, it's actually not the toddler's fault, not the preschooler's fault. It's just inevitable physics and chemistry that oftentimes we have these absorbed waters, but particularly things that are interacting with, oils on our skins or just the world in general. This thin layer of adsorbed water, oftentimes what ends up on top of that is a layer of polar organics. So what do I mean by polar organics? I might mean something, for example, like oleic acid. Right, they're innumerable polar organics, but for example, one of them is oleic acid, which looks something like this. There we go. Double bond. And then there's a COOH group right here. So what's the key thing here? This part is polar. The rest of it is non-polar. Polar. Right, this is made entirely of neutral carbon and carbon-hydrogen bonds, whereas here we have this polar stuff right here. And basically what happens? Well, the polar parts of these polar organics are attracted to the water underneath. So they all end up with the polar parts right here, for example, like the OH, and they all stick their nonpolar tails out towards the outside. And well, what just loves to stick to the nonpolar part? Well, nonpolar organics oftentimes end up around the edge. So what might we have next? We might have on the very top nonpolar organics. So, for example, that they might look like this, but just not with the OH group. So fully nonpolar things. And why might nonpolar organics be on the top surface? Well, if we think, what's at the very outside here is air. So, so if I were to just like plop a piece of metal out in front of you, and you were to sort of characterize what's going on at the surface of that metal, you actually wouldn't really detect metal at the surface. On top of the metal would be an oxide layer, on top of the oxide layer would be water, on top of the water would be polar organics, and then on top of the polar organics would be nonpolar organics. And it turns out that it's favorable for these nonpolar organics to interface with air. So take a moment now and pause and ponder. Why is it favorable for nonpolar organics to interface with air? Well, hopefully you've had a chance. Hopefully you've had a chance to think about it. If we think about what molecules make up air, air is made up of N2, which is like this, O2, which is like this, and this makes up almost all of the atoms that are in air. And if we think about this, even though oxygen is electronegative, when it's diatomic like this, these bonds, although nitrogen and oxygen are both electronegative atoms, both of these gases are nonpolar. Because when nitrogen is bonded with itself, they're each trying to pull those electrons towards themselves, but that ends up meaning that the bond is nonpolar. So what does it mean? It basically, if air is sort of the most nonpolar of them all, right? Air is an extremely nonpolar substance. So that means the most nonpolar of all of the junk that could end up on this surface ends up at the outside, interacting with air. So when we think about polar things, we think about hydrophilic and hydrophobic things. The nonpolar things interface with one another. These polar organics bridge the gap between nonpolar organics and water. Water essentially bridges the gap between polar organics and the oxide and the very polar oxide layer underneath. And this oxide layer is something that sort of inevitably forms on the surface of metals. So if you actually go to sort of try to characterize how hydrophilic or how hydrophobic a metal is, you're actually probably not characterizing how hydrophilic or how hydrophobic the metal is, but rather how hydrophilic or how hydrophobic all of this junk on the outside of the metal is. So a lot of times when you go to characterize surfaces, you might sort of try to develop intuitions about the bulk, but what ends up happening is, your measurements are affected by sort of how clean the surfaces are, right? And there might be, you might be able to use some very harsh solvents to try to strip off the nonpolar organics and maybe even the polar organics. You might be able to, prepare your samples in very specific ways to sort of avoid some of these layers forming. But, when you're doing these surface characterizations, this is something you gotta watch out for. It turns out this the effect of the environment, right? So the one effect of the environment can sort of be to dirty surfaces like this. Again, not the preschooler and the toddler's fault. It's just physics. That's what they could tell me later on. But the environment itself can have an effect on surfaces too. So let's take a moment now and think about how the environment might have might have an effect on the surface for polymers. So polymers. And in particular, obviously this isn't necessarily true for all polymers, but one example of a polymer is polyhema. So for example, polyhema, which is used in contact lenses. So it's that sort of the sort of clear gel. It forms a hydrogel when it absorbs water. But if you look at just what's happening with the polymer backbone, so within the repeat unit, there's CH2, and then a C, and then there's a CH3 up here. But on the other side of this carbon right here is a C double bonded to an O, a CH2, another CH2, and then an OH group off of this last one. So take a moment now, pause and ponder, highlight what parts of this repeat unit are polar. So and this is the repeat unit right here. So it then goes and repeats over and over and over again. So this is that carbon backbone that makes it up. So if I think about what parts of this polymer are polar, hopefully you've had a chance to think about it now, right? This carbon oxygen bond, that's going to be polar. And then this OH to a CH2, that part's going to be polar. Oh, sorry, I missed a part. Oh my God, I drew this molecule wrong. There's not a CH2. This C goes to an O, and then the O goes to a CH2. Sorry, there's not a bond right there. The C goes to an O, and then the O goes to a CH2. Oh my goodness, mistake. So what's the key thing here? This OC and this is also polar. So if I think about it, and basically if these are polar, okay, there's a slightly non-polar bond right here, but almost this whole side group is nearly all polar. Right, so this whole side group is pretty much polar, but the rest of this molecule up here is non-polar. So so what might that look like? Well, one interesting thing is these carbon-carbon single bonds can rotate. So interestingly enough, if you try to observe the surface properties of polyhema, its surface properties actually change depending on what kind of environment it's in. So let's say I had a blob of polyhema, and I put that in contact with air, which if you remember is very nonpolar. What ends up sticking out, basically all of these molecules all rotate to have their CH3 groups, their nonpolar groups, sticking out. But as soon as I take this polyhema and put it in my contact lens solution, or put it against my rather wet eyeballs, if I take this polyhema and then put it in contact with water, all of the polar groups end up turning themselves towards the outside. So I get all of the polar groups, all of these things right here. So basically, because this molecule rotates, if I put it in air, the molecule, like this would basically appear to be hydrophobic. It would appear to be a hydrophobic polymer. And if I put it in water, it would appear to be a hydrophilic polymer, even though it's the same polymer. It just sort of flipped itself around to change its state depending on what environment it's in. So this is something, you know, you need to consider. This is something you would also need to consider when you're trying to characterize the properties, right? You know, you could send the identical samples of polyhema to two different people, and one person would be like, oh, it looks pretty hydrophobic, and then you'd be like, well, how did you test it? And they're like, well, I tested it in air. And then, you know, you'd send it to a different colleague, and they'd be like, well, it seems really hydrophilic. And then you'd be like, how did you test it? And they're like, well, I tested it in water. And you're like, yeah, well, of course it looks hydrophobic in that case. Or sorry, of course it looks hydrophilic in that case. So the environment can actually affect it. So, you know, not just from the standpoint of actually physically putting junk on the surface, but even just the polymer itself can sort of orient itself and change what it, you know, how hydrophilic or how hydrophobic it appears to be, depending on the environment that it's in. So in this way, surface can differ from bulk, either by things being dirty or the environment sort of locally changing what's happening atomically at the surface. So now let's transition to talking about how we actually quantify how hydrophilic or how hydrophobic something is in a discussion of the contact angle. So the contact angle is one way that we use to characterize how hydrophilic or how hydrophobic surfaces are. So what do I mean by contact angle? Well, right here I have what's actually a lid to a canning jar, but on this I've put a blob of honey, and if you look at this from the side, you'll see that the honey, the honey stands up from the surface a little bit, and you might see that the honey I'm sorry, it's running all over the place, so forgive me for being vertical instead of horizontal, but you can see that there's an angle formed between the surface, which is flat, and the honey, the edge of the droplet of the honey comes up at some angle here. In a future lecture, I have some better visuals of what this contact angle is, but I just kind of wanted to give you a quick visualization of it right now. So, you know, what is contact angle? Well, contact angle, I have a solid surface. I put a liquid droplet on that surface, and oftentimes people talk about the contact angle, usually a contact angle of water with the solid surface, but again, you know, could be different things. So you put a liquid droplet on the surface, and then outside, you know, all around here, you have air, which sometimes, you know, in the literature, people oftentimes call this vapor. Just, you know, because I guess strictly speaking, it doesn't have to be air. But we basically sort of have three states of matter: solid, liquid, and vapor. And there exists surface tension anytime you or between any dissimilar materials. So there exists surface tension exists between dissimilar materials. And this surface tension acts to try to minimize to minimize the area of contact. So, you know, an analogy I like to do is, you know, I have my warm feet, and as I tiptoe across the kitchen floor to get a midnight snack, the floor's cold. So, you know, I try to pull my feet up and try to have as little contact between my feet and the floor as possible. Any dissimilar materials try to do that. You know, air and liquid and solid, basically air, you know, kind of for the regions we were talking about earlier, air is nonpolar, liquids can be polar or nonpolar. So the air and the liquids don't like to interact with one another. It's not sort of energetically favorable for them to do so. So liquids, tend to try to beat up in little droplets. A sphere is sort of the, for a given amount of volume of liquid, a sphere is the minimum surface area that can have. But then when you have three different materials, solids, which sort of have some rigid shape, liquids, which can deform their shape, and air or vapor, which can deform around the liquids, these basically, surface tension is basically a force which sort of drives the liquid and air interface to deform until it's sort of in a minimum energy state. So surface tension, you can think of it as a force to try to minimize the area of contact. So basically, and the way that surface tension acts is it's basically a force acting on a contact line. And this force acting on a contact line basically pulls to minimize the area. So contact angle essentially allows us to basically see, how favorable is the solid-liquid interface compared to the solid-air interface compared to the liquid-air interface. All of these interfaces are trying to minimize, and basically what shape the liquid droplet takes is some compromise between sort of all of these surface tensions acting on it. So how do we define contact angle? Well, contact angle is defined, you basically you choose a point where all three interfaces meet, you draw a line tangent to the air liquid interface, and you put your angle within the liquid. So basically theta contact is defined, within is the angle within the liquid phase, and tangent to the interfaces. Right, it's essentially tangent to the, if you imagine two lines tangent to those two interfaces at that contact point between all three interfaces, and within the liquid phase is that. So, and this contact angle usually specify, usually we use water as the liquid here, but you can use any number of liquids, organic solvents, alcohol, whatever. Oftentimes this contact angle allows us to sort of characterize how hydrophilic or how hydrophobic a surface is. So take a moment now, pause and ponder. For do we expect for hydrophilic surfaces do we expect a low contact angle or a high contact angle? Well, hopefully you've had a chance to think about it. For hydrophilic surfaces, these are, again, surfaces that like the liquid. We typically expect low contact angles. So basically what hydrophilic surfaces do is they basically pull the liquid towards them. It's favorable for the liquid to interact with the solid, and basically what that liquid, that solid essentially pulls the liquid down with a very low. So if you look at very hydrophilic substances, you can actually have the liquid sort of touched down, spread fully out. So this phenomenon is called fully wetting. fully wetting. And this basically occurs for very hydrophilic things. Surface solids. Then, not there, you can have something that's hydrophilic, just maybe not quite so hydrophilic as to fully stretch the droplet all the way out. You could also have a solid surface where maybe it doesn't fully wet out, but you have this droplet have the liquid droplet basically takes a very shallow angle. So this would be a small contact angle. And then you can even have solids, for example, very hydrophobic ones, where this contact angle can be obtuse, right? Can be maybe even almost a full 180 degrees. So you can have, you're still drawing it, you're still defining that angle within the liquid phase. And it can sometimes be almost a full 90 degrees, right? So you might have heard of like super hydrophobic polymers, or like Rain X, which is a product that you can put on your windshield to basically make the rain beat up and shed off of the surface instead of, make your vision all blurry by sticking to the surface. Rain X basically makes your windshield very hydrophobic. So if we sort of put these on a spectrum, these ones are hydrophilic, and these ones are hydrophobic. And this is something you can observe experimentally. You can take your surface, you can put a droplet on it, you can get a macro lens or a microscope or something like that, and zoom way into the edge of the droplet, take a picture, do some image processing, or even just take out a protractor and measure these contact angles. And that gives you a metric of how hydrophilic or hydrophobic is. Of course, you don't even need to do it yourself. A lot of people have already done this for common materials, so you can just Google online contact angle for many common materials, and you can look them up. And oftentimes, if you look at the molecular structure of these polymers, oftentimes, you can look at it and you can see, ones that have lots of carbon oxygen or carbon nitrogen bonds, those ones tend to have small contact angles. Or other polymers that tend to be mostly carbon hydrogen bonds, those tend to have really high contact angles. And trust me, like it's clear as day. You can look at the type of polymer, look at the contact angle, look up the molecular structure, and it's clear as day. You can see basically like it's almost down to like what fraction of the bonds are carbon hydrogen or carbon carbon versus carbon and something more electronegative, and you can pretty readily predict which ones are fully wetting, which ones the material would sort of beat up on. Now you might be saying, geez, Lannon, like you're talking a whole lot about these surface characterizations. Like, why do we care, right? Like, who cares about whether surfaces are hydrophilic or hydrophobic? So there are a couple of applications that we might care about. So one application where we care about whether something is wetting or not wetting is wound dressings. So, if a patient is bleeding, you might want something to sort of absorb a lot of that blood so you can actually see what's going on with the wound site, or help clean wounds, things like that. It turns out we'll talk about this in actually a future lecture, but hydrophilic surfaces tend to be non-fouling. So if you're looking to sort of, if you're looking to, have maybe like the interior of a bioreactor, or you're looking to, design an implant that would resist a bacterial biofilm forming on it, or, implanting something into blood, the hydrophilic surfaces are basically the ones that tend, we'll talk about this in a future lecture, but the ones that tend to have less protein adsorption. And less protein adsorption means bacteria don't stick. It basically means that like platelets and thrombin and stuff like that don't get activated. So, we might care about these things for like wound dressings, for sucking up fluid. We might care about these things for implants or bioreactors to make them non-fouling. There's also a lot of cool work being done on paper microfluidics. So paper, where basically you can have, instead of having sort of expensive microfluidic devices, you can basically make chemical assays out of paper, where you sort of like, dip this paper microfluidic device into some biological sample. The hydrophilic paper wicks the fluid through a series of chemical reagents or antibodies or other things like that. This is essentially how a pregnancy test works. So basically, sort of by choosing the right materials to make your wicking agent out of, you can control you can prescribe the flow rates and things like that to basically design assays, for example, like pregnancy tests. And then the final thing that we might care about for these things here is 3D printing. So when the bead of 3D printed ink, whether it's a bio ink for a 3D bioprinter or polymers or other things like that, it's oftentimes this sort of wetting and surface agent. You essentially have liquid, i.e. like the resin or the molten polymer coming out. Oftentimes, basically how much that polymer sort of beads up versus how much it smears down on the surface controls what size and shape features you can create. Make it too wetting on the surface and it just sort of smears itself out. Make it too hydrophobic and your layers don't stick to one another, because essentially it just beads up on top of the layer instead of sticking to it. So we care a lot about surface tension, contact angles, things like that in terms of 3D printing and sort of being able to maintain accurate feature shapes. So this, we care about this stuff. This is our bread and butter. These are some of the most important aspects of bioengineering. So finally, let's talk about the last topic of today, which is the interpretation of contact angle as a force per length. So I said earlier that that surface tension pulls on a surface, and it pulls in such a way as to try to minimize it basically pulls in such a way that it tries to minimize the contact area between certain things. But it's a balance. So surface tension, it sort of pulls. You can think of surface tension pulls inward on a surface at the contact line, and to try to minimize its interface. But it oftentimes ends up opposing, at an interface between solid, liquid, vapor, we end up with sort of a three-way tug of war, a three-way fight between multiple interfaces, and oftentimes we end up with an equilibrium here. So at this interface, we basically end up with equilibrium between three surface tension forces. So what do I mean about an equilibrium? Well, just imagine I had a droplet whose sort of default contact angle, imagine I had a droplet whose sort of default contact angle would, let's say, be 45 degrees. So let's say, imagine I had a droplet here, and this droplet likes to form a 45-degree contact angle. Well, here I have the solid, here I have the liquid, and here I have the vapor, i.e. air. So what happens? Well, there's a surface tension force between vapor and liquid that pulls on this contact line this way. So basically the surface tension between these is basically pulling this contact line this way. There's a surface tension force between the liquid and the solid that's trying to pull that one as well. So actually, let me just put the, so basically the liquid vapor surface tension pulls this way. The liquid and essentially it's trying to pull this contact line up off of the surface. Between there's surface tension between the liquid and solid, and the liquid solid surface tension pulls this way, is essentially pulling the contact line along this way. But there's also surface tension between the solid and vapor, and the solid vapor surface tension basically pulls it this way. So you can imagine there's this sort of three-way tug-of-war where, you know, these two are sort of tugging it this way, this one's tugging it this way, and at an equilibrium we'll get our contact angle between these two. So, you know, if let's say there's this default contact angle of, let's say, 45 degrees for this particular combination of liquid, vapor, and solid, if, you know, let's say I first put that droplet down, you know, let's say this droplet, you know, let's say when I first plopped this droplet down, it started off with one that was too high. Well, the liquid vapor is pulling like this. You know, it's oops, sorry, I drew this wrong. Ignore this. Right, so let's say initially this one's pulling up like this, this one pulls out like this. You know, initially this is out of equilibrium. You know, if the contact angle is too big, then this pulls. It basically pulls that edge of the droplet outward until it's until at 45, until at its equilibrium contact angle. Similarly, on the other end, you know, let's say you know, I took a squeegee and I squeegeed this droplet out, you know, sort of temporarily making this contact angle below what its equilibrium would be. So if I temporarily made it below what its contact thing, then all of a sudden I have two forces. You know, if I sort of temporarily made the liquid too short of a contact angle, then this basically gets pulled this way. Basically, the contact point gets pulled this way. The contact point gets pulled this way until it sort of is back at its equilibrium here. And of course, different materials, you know, different combinations of liquid, vapor, and solid have different sort of equilibrium contact angles. So, you know, when you do an experiment, you oftentimes put a droplet and then jiggle the surface in some way to, like, sort of make sure that droplet is kind of in its equilibrium configuration. And basically, measuring the contact angle basically tells you, you know, is this surface tension so big such that we need, we need this surface tension, on this side to sort of balance it out this way, or is this surface tension so big that we need these two to balance it out? Basically, the contact line shifts around until the droplet has basically warped into a shape where it's sort of in its equilibrium contact angle. And when we do it, you can kind of imagine sort of this happening qualitatively. Surface tension has this interpretation. If you look at surface tension, it has units of force per length. So surface tension, it basically has units of force per length. And how do I want you to sort of interpret this? Well, there are a couple ways to sort of interpret this. One way is to sort of imagine, here I've sort of imagined drawing cross sections of this interface here. So just imagine I had sort of the weirdest droplet ever, where I had a solid surface that looked like this. I'm going to attempt to draw 3D for a moment, and then just imagine I had a droplet on that surface, that kind of looked like this. So imagine I had sort of a weird hemi-cylindrical droplet. If I had this weird hemi-cylindrical droplet, you could imagine doing a force balance on this line. So do a force balance. On the line. So I'm gonna return to sort of this side view right here. So here I have the line. Here's the solid surface. If I kind of draw it from this side, here's the liquid interface here. Surface tension is oftentimes given the Greek letter gamma. And then oftentimes it's given subscripts, and those subscripts basically denote whether, sort of what part of the surface tension it's in. So it might. So for example, if I were to sort of look at this interface right here, along this line, along this line, I would have the liquid vapor surface tension. And then along this line, so, again, the fluid is right here. Along this line, I would have the liquid solid surface tension to denote that this surface tension is acting on the interface between the liquid and the solid. And then this one, I would have the solid vapor surface tension. So basically, you use the two subscripts to describe whether it's in the solid, the liquid, or the vapor. The solid, liquid, vapor phases, and the liquid solid pulls on the interface, or pulls at the contact line along the interface between those two. And if we think about doing a force balance, on this interface right here, let's do it in the x direction. So let's call x and y. So we'll do our force balance in the x direction. Well, you can imagine if I had some length, let's say I had some length L of this contact line, the force balance, well, it would be if it's sort of this, the force per unit length is acting on this whole line here, and surface tension has units of force per length, so I get the force in the x direction from this would be L times the solid vapor surface tension, and that's acting in the positive x direction. In the negative x direction, I would have minus, in the negative x direction, this surface tension is also acting over a length L. It's also acting over a length L, and it's also acting purely in the negative x direction. So I have my liquid-solid interface right here. And then here, I have my contact angle right here. There's an x component of this force, of the liquid vapor force, acting in the x direction. So, and that's acting in the negative x direction, and that's acting over a length L. So I still have L times the liquid vapor surface tension, but this also needs to be multiplied by, well, what relates this angle to sort of give this component of it? It would be cosine of my contact angle. And those three basically need to add up together to equal 0. If we notice, we can sort of divide out L from all of them, and you can sort of you can do a little rearranging if you want, but you can basically say the liquid or the solid vapor surface tension ends up being equal to the liquid solid surface tension plus the liquid vapor surface tension times the cosine of the contact angle. So what's going on here, basically from a contact angle measurement and some a priori knowledge, for example, about the liquid vapor surface tension, you can try to find, you can't find them independently, but you can at least find how these other surface tensions relate. So you can basically do some measurements, bring in some known values, and then try to infer maybe not what these properties are exactly, but at least what they are sort of in combination. So so this is an equation that you can sort of relate quantitative things in terms of force per length to something that you can observe experimentally, like a contact angle. So so there we have it. And so what how might we observe this in in real life? Well, it turns out that you can actually observe some of these effects, some of this effect of surface tension in real life. So for example, if you have a bubble, let's do a little aside over here. If you have a droplet of fluid, let's say a droplet of fluid, it turns out that the pressure inside of this droplet is actually higher than the atmospheric outside, out here, right? So let's say I have atmospheric pressure out here. The P inside is actually greater than atmospheric pressure. Why? Well, if you imagined, if I took this bubble and sort of sliced it like this, and imagine sort of a hemisphere, imagined a hemispherical half of a bubble, surface tension, the liquid vapor surface tension of this droplet is essentially pulling, it's sort of along the equator of this, it's basically pulling the two halves, it's trying to pull the two halves of that surface together. Surface tension is basically pulling here. So surface tension is basically pulling like this. So what does that mean? Well, that if I were to imagine, there's no net force on this bubble, right? It's not going anywhere. So what does that mean? Basically, I need pressure. So basically, pressure is sort of pushing down on the inside, and this happens both with bubbles. That's sort of a thin liquid or a thin liquid film with gas inside and gas on the outside. This is why when you pop a bubble, the bubble actually pops outwards. It's because it's pressurized inside. And this also happens with liquid droplets too. So if you're trying to like create emulsions or things like that, it's actually higher pressure inside of a droplet compared to outside. If you were able to stick a little magic pressure probe in there, you would actually measure a higher pressure inside. And that's basically due to this idea that for surface tension, the force acts on the perimeter. The surface tension essentially acts on the perimeter of the surface here, and basically the pressure acts on the area, and these two are in equilibrium for bubbles that are not changing their shape, you know, not expanding or contracting. So thanks again for watching. Hopefully you've learned a little bit about surface hydrophobicity and hydrophilicity, and how surface properties can differ from bulk depending on how they've been affected by their environment, and also similarly learned about how we start to quantify these things in terms of what the contact angle is, what surface tension is, and in particular how surface tension has an interpretation of force per unit length. Thanks for watching, and good luck with your study of biomaterials.